Alright gang, here we go. This is for Chem 2 Unit 11. We're talking about weak bases and the relationship between Ka and Kb. Alright, so weak bases are everything that's not a strong base. Alright, all bases that aren't a strong base. And they're weak because they do not ionize completely. Oops, I forgot. I don't have my pen up. Anyway, all right, so like weak acids, weak bases have an equilibrium constant, but instead of it being an acid dissociation constant, we call it a base dissociation constant, Kb. All right, equilibrium calculations will work the same. All right, however, with a slight difference. Instead of it acting like an acid and donating that proton, it's going to act like a base and accept a proton. So this ammonia reacts with water to form this guy here. So the Kb is always going to look like this. All right, so so before we had the generic weak acid formula, something like Ha plus H2O was in equilibrium with H3O plus A minus, right? That was our generic weak acid equilibrium. And then we have the same kind of idea for our generic weak base formula. I've seen it written several different ways, but it would be something like this, like whatever our weak base is plus water is going to yield. It'd be OH minus plus B plus, right? Or you could start with a B minus over here, and then it would be neutral on the other side. 6 of one, half dozen of the other, whatever floats your boat. Essentially what happens, though, is your conjugate acid from your weak base and your hydroxide are going to be in the numerator, and then you have your original base, your weak base is going to be in the denominator, all right? Your little dissociation constant. All right, there's two real types of weak bases, that are neutral substances, okay, and these guys that have a non-bonding pair of electrons. So that's like your ammonia, right? Your ammonia structure, you've got your nitrogen, your 3 hydrogens, and then there's the lone pair that's sticking up there like that. And your methylamine is the same way. But then you also have anions of weak acids, which would be their conjugate bases. So like something like acetate, CH3COO minus. All right, this guy would be a weak base, and it's the conjugate of the weak acid, acetic acid, vinegar. All right. So your base dissociation constants work exactly the same as the acidic dissociation constants, the Ka. Okay, the bigger that Kb value, the stronger of a base it is. All right, so here's ammonia. It's 1.8 times 10 to the minus 5th, a fairly big base. All right, pyridine, 1.7 times 10 to the minus 9th. All right, so on and so forth. All right, here's your conjugate acids. Essentially all you have to do is just add a hydrogen and then raise the charge by 1. If it was 0 before, neutral, you just add 1, becomes plus. Pretty easy. All right, here's some more Kbs. Here's hydrogen sulfide, becomes hydrosulfuric acid. All right. So now we want to be able to calculate the pH of a weak base solution. So this is pretty easy. So here's our general formula, okay, and this is going to work very, very similar to the weak acids. All right, we're just going to use our ICE table here in order to calculate our concentration of hydroxide. All right, so here's our ammonia. Here's our initial concentration at 0.15, starting with 0 ammonium, 0 hydroxide. This would go down by some amount, up by some amount. 0.15 minus x, and then so this is our base dissociation. We can just plug these guys in. So this would become x squared over 0.15 minus x, and this is equal to 1.8 times 10 to the minus 5th. Now the nice thing is that because this is times, this should be an exponent times 10 to the minus 5th. So we'll put a little exponent symbol. All right. Because this is times 10 to the minus 5th and this is 0.15, this x value would have to be much, much smaller than this, so we can neglect that. So it becomes this nice, easy thing here. All right, and so we can solve for x, and so our x value is equal to 1.6 times 10 to the minus 3rd. Now remember, this x value was equal to the concentration of ammonium and hydroxide. Okay, but they asked for the pH. So in order to find the pH, there's a couple of different things we do, right? We remember from before that the pH plus the pOH, all right, is equal to 14. So we could take the negative log of this value, all right, and then subtract it from 14, and that'd be our pH. So that's what they did here. Or remember, we can use the concentration of the hydronium plus times the concentration of our hydroxide. should be equal to 1 times 10 to the minus 14th. Right, so we could use this guy. We could take this x value, which is equal to the concentration of hydroxide. All right, plug that in here, solve for the concentration of hydronium, and then take the negative log of that. Really, it's 6 to 1, half dozen the other, because really these two are the same. We've just taken the negative log of this reaction up here. All right, so let's see if we can do a practice problem here. Okay, it says, what is the pH of a 0.65 molar solution of pyridine? All right, so pyridine has a Kb of, and we're gonna write this guy down and then make that table go away. All right, because I'm pretty sure I was right. All right, so 1.7 times 10 to the minus 9th. All right. Oh, and we lost our, oh well, we'll have to pull it up here in a second. So what is the pH of that solution of pyridine? All right, C5H5N. So we've got C5H5N plus water is going to form OH minus plus HC5H5N plus. All right, we got our ice table, ICE. All right, initial concentration of pyridine is that 0.65, so I'll throw that guy in right there. Water, 0, 0, doesn't matter. Hydroxide concentration is going to be 0, and so is the pyranic acid. Okay, so this is going to go down by some amount. This is going to go up by some amount and some amount. And we know this is all 1 to 1 because this is a balanced chemical equation. So this becomes 0.65 minus x, and then x. So our Kb is going to be equal, well, we just wrote it down right here, so that's the 1.7 times 10 to the minus 9th. All right, and this is going to be equal to x squared over 0.65 minus x. All right, minus x. Now, we see that this is 0.65 minus x, so if we were going to write this in scientific notation, it would be 6.5 times 10 to the minus 1st. This guy is times 10 to the minus 9th, so we can for sure neglect this x. We can get rid of that sucker. So really it just becomes x squared over 0.65. All right, so multiply 0.65 over, take the square root, and our x is equal to, so we take 0.65 times 1.7 e to the minus 9th. Take the square root of that. All right, and I got 3.32 times 10 to the minus 5th. So that's the concentration of the hydroxide, but it wants the pH. So in order to find the pH, what we have to do is we'll take pH. Remember the pH plus the pOH, we just established this just a second ago, but just to recap, this plus that will be equal to 14. So our pH should be equal to 14 minus our pOH. And our pOH is our negative log. So we take 14 minus the negative log of this concentration we just got, which is the 3.32 times 10 to the minus 5th. All right, so that means our pH would be equal to 14 minus the negative log of the answer that we just got. So I got 9.52. How many sig figs? 2 sig figs, so 9.52. Is that an answer option? It is. Hallelujah. I always get nervous about that. All right. One last thing here, relationship between Ka and Kb. All right. Just take a second, pause the video, and what I want you to do is just take a Ka, all right, times the Kb and see what you get, and do that for a couple of them. All right, hopefully you did that, and you should notice that when you do that, you get this weird idea, that you get this thing that Ka times the Kb is equal to 1 times 10 to the minus 14th, and that should look really familiar, because that is 1 times 10 to the minus 14th is your Kw. So we get this cool relationship between any conjugate acid-base pair. Ka times Kb is equal to Kw. So if we want to find one of them, really we just have to divide the other one by, or divide Kw by the other one. So let's, we're going to walk through a practice problem here that they do. So they say calculate the Kb for the fluoride ion and the Ka for the ammonia ion. All right, so it says for the weak acid HF, table 16.2 in appendix D, give this value for the Ka. All right, so there's your Ka of your HF. Well, if you want to find it for the Kb for it, all we have to do is divide the Kw by our Ka. So 1 times 10 to the minus 14th divided by 6.8 times 10 to the minus 4th. And so this would be the Kb. All right, and then we can do the same thing for ammonium, but now we're calculating the Ka, so we or the Kb, or we're starting with the Kb for ammonium. So this would be the Kb for ammonium, 1.8 times 10 to the minus fifth. All right, this is just from that table 16.4 that we just looked at just a second ago. So to find the Ka, you simply divide 1 times 10 to the minus 14th by that value, and we get that value there. All right, and we could look up the Ka for ammonium, and it would match. All right. And that's it for this video. We did some weak base problems here, finding the pH value, and then we also compared Ka and Kb. Do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.